Okay, so what I have here is a pretty powerful electromagnet. Right now it's not connected to the power supply, so there's no current flowing. When I do connect it, then the current flows to a tightly wound coil. You can't see it, but take my word for it, there's a tightly wound coil that's in here, and I think you'll believe that's true when you see the way this operates. When I take and put these together, there's no interaction between these pieces of metal, but as soon as I complete the circuit, then adding an electric current to the coil makes for some magnetism. And in fact, so much magnetism, I can't pull these apart. I can try as hard as I want, they're not coming apart. I bet it would support my body weight. I haven't tried that one, but I suspect that would be the case. As soon as I disconnect, magnetism goes away when the current goes away. So that's just meant to illustrate this idea that anytime you add a current to a coil of wire, the result is you get some magnetism. You might be able to appreciate that better with this demonstration. Here you can see the coil involved. So if I take and disconnect that part of the circuit to the battery, I can connect to the coil, and at this point there's no current at all in this coil, and we can show that by bringing it near some paper clips and seeing it doesn't pick them up at all. As soon as I complete the circuit and allow a current to flow in the coil, then it should have some magnetism. Sure enough, it picks up these paper clips. As soon as I disconnect, the paper clips all fall away. So yeah, current added to a coil makes for magnetism. Now that's got me thinking, and it begs the question, does that operate in the reverse process? If I take a coil and bring a magnet near it, will that make current start to flow? Seems like a fair enough question, and it turns out the answer is no, it doesn't work like that. So we can try that. I have, well, this is really just a metal rod, but as soon as I attach a magnet to the metal rod, then I magnetize the whole rod, and we can see that. Again, bring it near the paper clips, and it picks them up. If I get rid of that magnet, and they fall away. So think of this whole thing as one extended magnet. And then we have a coil of wire. Now, the coil of wire has a connection to this device, but this device is in no way a power source. In fact, this is a very sensitive ammeter. If any current is flowing in this coil, then this meter will register it. And sure enough, the meter shows 0. We wouldn't expect to have any current flowing in a coil that's not connected to any source of power. So let's try something. Let's bring the magnet near the coil and see if that makes electricity. No, doesn't do it. So it was a fair guess to think that anytime I add current to a coil, it makes a magnet, then maybe that means anytime I bring a magnet near a coil, that makes a current. Not quite, but almost. That's almost correct. Let me show you something you've seen before, the DC motor. So with the DC motor, if I turn the switch on, now I'm putting electrical energy into the system, and what I get out is mechanical energy. That's the idea behind all motors. Electrical energy input leads to some motion, some mechanical energy output. So does that process work in reverse? Yeah, absolutely. In fact, that's the basis behind all generators. A generator puts mechanical energy in and you get electrical energy out. So let's come back to our coil of wire connected to our sensitive meter. And indeed, just bringing a magnet near it doesn't do anything. But if I can bring mechanical energy, then maybe I can create some electrical energy out. And here's the deal. As long as I change the amount of magnetism with the coil, then it creates electricity. You can see the needle move as long as there's motion. Now right here, there is magnetic field passing through the coil. In fact, there's a name for that. We call that magnetic flux. When a magnetic field passes through the cross-sectional area of a coil of wire, we say that coil of wire has a magnetic flux. So magnetic flux is measured in Teslas times square meters. It's just a magnetic field strength multiplied by a cross-sectional area. Notice that magnetic flux does not make electricity. However, whenever that magnetic flux is either decreased or when that magnetic flux is increased, you do generate electricity. So that's known as Faraday's law of electromagnetic induction, and it says that a change in magnetic flux produces an induced voltage. Flux by itself doesn't do anything, but as long as there's a change in flux, I can create electricity.